All right, hello, welcome back to our conversation about solutions, namely the way that chemists describe solutions. We just spent a couple of time in our past few lecture videos talking about molarity and the idea of concentration and how we can use concentration to describe a solution according to its amount of moles of solute per volume solution. And we also talked about how we could use the unit of molarity, right? That concentration unit of molarity in moles per liter to convert between moles and liters as needed. So that was one of our intensive properties, meaning like it doesn't change regardless of how much of your substance you have, of solutions that we use as chemists to describe those solutions. The next intensive property we have is density. So let's remind ourselves about the definition, DEF, of density, like generally, not necessarily relating to solutions, but just generally. So if concentration is a proportion of moles to volume, and molar mass is mass to moles, then density is a proportion of a substance's mass and volume. And in this class, if it's like a solid, we'll see that in grams per cubic centimeters. And if it is a liquid, solution, or gas, so AQ, aqueous, then we will see it expressed as grams per mil. These are effectively the exact same unit because 1 milliliter is equal to 1 cubic centimeter. But just to, kind of keep our technical definitions in place, wanted to bring that to your attention. So thinking back to when we talked about molarity as being a proportion of moles and liters. Density is a proportion. It's just a proportion of two different things about the substance. So for a solution, this has to be a proportion of the mass of solution related per volume of solution. So writing out density of a solution specifically, this would be the mass of the solution itself in grams over the volume of the solution in milliliters. And this quotient or this ratio is what makes us a proportion. And here we have our definition of density now expressed specifically for solutions. Now, while this might seem like some pretty old review, like didn't we learn this in the first week of Gen Chem? You're right. However, again, please take special care when you're identifying what you're talking about when labeling these variables. So if we're talking about density of a substance, it is the mass of the substance, not the components of the substance, right? Not a part of the substance, but the entire substance itself divided by its volume, or how much space that substance takes up. Because you'll see when we start talking about concentration, right? We're talking about like piece or part over whole, solute over solution, solute over solvent. In density for solutions, we're talking about mass of the solution in its entirety per volume of the solution in its entirety. Let's remind ourselves of something that is kind of like a core law of the universe. So recall the law of conservation of matter. We have talked about this before. the mass of solution is going to be equal to the mass of the solute plus the mass of the solvent, right? Mass is conserved. If I've got 5 grams of sucrose that I dissolve in 10 grams of water, I should have 15 grams of solution. My total amount of mass should not change. That would be breaking the rules of physics. So if it helps you to maybe put this in to your numerator, you can. But I think this is more of like a general rule that you should just have in your back pocket for when maybe you aren't outright given the mass of solution. Now, this is not true for the volume. Volume's not necessarily additive. We could relate it to mass by the densities of each of the respective solute solvent components in solution. So we're going to just go with law of conservation of matter via a law of conservation of mass. Okay, practice using density. So we've got some lemonade. How refreshing. So lemonade is a solution of lemon juice, water, and sugar. Okay, so I'm just going to start identifying some things about my solution. So let's look at the solutes. So I have multiple solutes here. Lemon juice and sugar are the things that you dissolve in water to make lemonade, right? So my solutes are lemon juice and sugar. And let's go hunting in the problem for some information about lemon juice and sugar. So continuing on, lemonade's a solution of lemon juice, water, and sugar. If 20 mils of lemon juice, so I know that I have 20.0 milliliters of lemon juice, and I'm given a density of density 1.33 grams per milliliter. That looks like a mole. That is milliliter. Okay, anything else about lemon juice? Nope. So then let's see here. Let's go to our other solute. So we've found our information about lemon juice, solute. Let's now look at our sugar. So our sugar, we know the mass is 10.5 grams. All right. What does that mean about our solvent? So water is the solvent here. This is the thing that is dissolving our solutes. So this is our water. What information were we given about water here? So we knew that we had 750 milliliters of water. And we also know the density of water, specifically tap water. Seems a little low, but that's okay. Grams per mil. And then we're going to identify our goal. So this is just a different approach to the problem. Instead of identifying your goal first, we've kind of pulled out threads of information, and now we're going to bring them together for the bigger picture. So the goal is to find what? Let's see here. What is the density of the lemonade solution? So our goal is we want density, which is mass solution over volume solution. Okay, let's pay attention to this little note that comes after our goal. So what is the density of the lemonade solution? Assume that when the sucrose dissolves, the total volume is not affected. So kind of a similar assumption that we made when we were looking at the concentration of a sucrose solution in our molarity concentration calculation, right? We assumed that the total volume of solution was equal to the volume of water. Here, we need to just ensure that we're thinking about the total volume of everything. So let's see here. Density of a solution is equal to the mass of solution over the total volume of solution. And we know that the mass of solution is going to be the mass of all of its components, right? Mass of solutes over the total volume solution. And I forgot my solvents in my numerator. So mass of solutes and solvents together over the total volume of solution. So we need to identify the mass of our solutes. So the mass of our lemon juice and our sugar. And then the total volume of solution. And remember, like, yes, we know how much water we use to make our lemonade, but that's not the only liquid that was used to make lemonade, right? We also use some lemon juice. So let's take the next slide to try to get total volume of solution and mass of solutes and solvents together. Okay, so what is the density of the lemonade solution? So mass of solutes is equal to the mass of lemon juice plus the mass of sucrose. Going back to my information that I had gathered in the first part of this problem, the sugar, I know exactly the mass that I added. Like I already have this. This was given to me in the problem. No conversion is necessary. So I have my 10.5 grams of sugar. And now I need to find the mass of my lemon juice. Now, looking at the information of my lemon juice, I was not given, like I was with sugar, a total mass. Rather, what I was given was a volume of lemon juice and the density of lemon juice, which relates mass and volume. So I'm going to have to convert this volume of lemon juice, this 20 milliliters, into a mass using my density. So we have the mass of the juice. That was our 20.00 milliliters of juice times, using our conversion factor, our density was 1.33 grams per 1 milliliter. So 1 milliliter of juice weighs 1.33 grams. So 1.33 grams per mil times 20 milliliters, keeping our sig figs 26.6. That's all right. It's an exact number there. Grams of juice. This is going to go up here, 26.6 grams. So in total, our mass of solutes is equal to 26.6 plus 10.5. This gives us 37.1 grams of solutes. Now, if we're trying to find the density, this is again mass of solution over volume of solution. And the solution itself is made of mass of solutes and solvents. So we now need to figure out our mass of solvent. So that's our water. And going back to our information that we know about water, very similar to what we knew about our lemon juice, right? We were given a volume and a density. So we had 750 milliliters with a density of 0.99. Honestly, this density is probably not right for tap water. It's probably closer to 1 gram per mil, but we'll go ahead and use it, 0.9979. So we've got to figure out using a conversion the mass of solvent. So this is our 750.0 or just point milliliters of H2O. We want grams and we would like to cancel out milliliters. So 1 milliliter of tap water weighs 0.9979 grams. So I take my 750 mils, multiply it by my density, and that gives me 748.42. And I'm just gonna, let's see here, 425, show all my digits for now. Grams of water, which means that the overall mass of solution, so this plus this, is equal to mass of solution so we've got our 26.6 grams of lemon juice. One of our solutes plus the 10.5 grams of sucrose, sugar, plus our mass of our solvent. So let's see here. We were limited to 3 sig figs, so 748 grams of water. So let's add this all up. We have 748 blah, 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 plus 26.6 plus 10.5. Completely unrounded, this gives me like 785.5. But I want to limit myself, since I'm doing addition here, to no places after the decimal. So that would be to the nearest ones. So when I do this, I get 785.5 grams of solution. With the proper sig figs, that is going to be 786 grams solution. But since we need to use this mass later, we're going to keep it in its unrounded state. All right. So we have our total mass of solute and solvent, meaning we have our mass of solution. And to find the density, we need the volume of solution in milliliters. So we need to think about what happens if I were to take 750 mils of my water and add to that 20 mils of juice. So my total volume of solution. Consider all liquid or aqueous components. So my volume of solution. This is going to be the sum of my volume of juice and my volume of water. So that was for our juice, I believe it was 20.00 milliliters. And our water was our 750. Milliliters. So this gives us 770 milliliters. And now let's find a little spot to figure out our density, because now we have mass and volume. So here is our solution mass right here. And now we have our solution volume. So this is equal to 785.5 grams over 770 milliliters. I know that I'm going to have to limit myself to 3 sig figs. So I get a solution density of 1.02 grams per milliliter for this lemonade solution. So our density was 1.02 grams per milliliter. Okay. We can, just like we have done with our molarity videos, is we could practice using density as a conversion factor between mass and volume. I think that is something that we will just be doing enough of in the future. So I think we'll kind of like skip over that for now. So what I really want you to get out of this slide is the idea that when we're talking about the solution, we're talking about everything in it, right? Solute, solvents. So if I want the mass of the solution and I know what its components are, I need the total mass of the components. And then if I want the total volume of solution, I need to consider the total volume of components or either what's given as a total volume solution. So you have to think about like what is actually being made here. A good way to do this, like, I've drawn this really cute little lemonade solution, but a good way to kind of remind yourself of what's going on is to sketch out what this might look like. So if you add 20.00 milliliters of lemon juice, and then 750 milliliters of water, right? This will give you a sense of what the total volume is. And then if you think about the total mass, you have to remind yourself that these 3 components here in our solution all contribute toward the total mass. So a little diagram like this can go a long way in helping you out with these problems. Okay. So we have reviewed now how chemists describe solutions via some of their important intensive properties, namely their concentration and their density, concentration and molarity and density. Coming up, we are going to look at how we can maybe express concentration in different ways. So while molarity is incredibly useful, it's not necessarily the most useful unit in every single circumstance that we might encounter in the lab. So there are some other solution units that I would like to introduce you to, which you can find coming up in our next discussion.